So in this video, I'm going to show you the solution to one of the homework problems you guys asked questions about, which was from assignment number 18, problem number 57. So the question says, on what intervals is the function f of x equals x to the fourth minus 4x cubed, both decreasing and concave up? We're going to go beyond that question, and we're also going to sketch a graph for this. So the first piece that I'm going to do to sketch my graph would be to find my x-intercept. So set your original function equal to 0, factor it, and find the values of x, which would give that a value of 0. Now, if we were just answering the question, we would not necessarily need to do that, but we're going to go above and beyond. Now, the next piece is we're going to analyze our slopes. So let's take the first derivative. So the derivative of x to the fourth is 4x cubed. The derivative of 4x cubed is minus, we have a minus 12x squared. And then what we're going to do is set that equal to 0 to find some critical points. And so our values for that would be at 0 and 3. And then finally, we're going to analyze our second derivative to help us gather some information about concavity. And so let us take the second derivative, which would be f double prime of x is equal to 12x squared minus 24x. And once again, we're going to set this equal to 0. And I'm going to factor out a common factor, which give me values of 0 or 2. Now, to get a general idea of what this graph is going to look like, what I'm going to do is take all of these important points, 0, 3, and 2, in other words, the places where the first and second derivative were equal to 0, and use those boundary points to set up intervals that I'm going to check. And to be able to organize all of my data, I'm going to put myself, I'm going to make myself a number line here. I'm going to place the values where the first derivative was 0, as well as where the second derivative was 0. And then what I'm going to do is I'm going to test each of our regions, and I'm going to test it for both f prime, and I'm going to test it for f double prime. And then this way, it will allow me to assess whether my function was increasing or decreasing, concave up or concave down. So it's easiest to do this if we plug it into the factored form. So I'm going to take the factored form of the first derivative, 4x squared, times, choose a value of x that's less than 0. So say, for example, we choose -1. And I'm going to plug -1 in there. And into my first set of factors, I get a positive value. If I plug -1 in the second, I get a negative, and a positive times a negative gives me a negative overall. So I'll wait a moment to do the analysis all at the same time. So right now I'll just check the signs of each of the regions. Now, plug in a number between 0 and 2, so let's plug in 1. Now, 4x squared is always positive. If I plug in 1 into the second parenthesis, I get a negative, so a positive times a negative is a negative. Plug in a number between 2 and 3, so like 2.5 would give me a positive times a 2.5 minus 3 would give me a negative. Therefore, in that region, the overall first derivative is negative. And let's plug in a number bigger than 3, so 4, and both of the cases would give me a positive. So therefore, for function f, it will be decreasing because my first derivative is negative, decreasing again, and then finally on the last interval, my function f is increasing because my first derivative was positive in that region. Now let's go ahead and analyze the second derivative to be able to discuss the concavity of our function. So I'm going to take the factored form of our second derivative. So 12x times x minus 2. And I'm going to plug in a number less than 0. So let's choose -1, for example. And that would give me a negative times another negative, which gives me a positive. And let's choose a number between 0 and 2. So let's say 1, for example. That would give me a positive times a negative, which gives me a negative. And a number between 2 and 3. That would give me a positive times a positive, which is positive overall. And finally, a number greater than 3 would give me positive in both those factors. So therefore, my original function was going to be, for x less than 0, it was going to be concave up. Then between 0 and 2, concave down. Then concave up between 2 and 3, and concave up. Now let's go ahead and sketch a graph. And so I'm going to put down values on my x-axis that correspond to some of my important points. And then I'll plot my x-intercepts, which I originally found to be 0 and 4. And then I'm going to plot values between those pieces on those. And first I do decreasing concave up, then decreasing concave down, then decreasing concave up, then increasing concave up. Now, to answer the original question, the places where my graph was concave up and decreasing are highlighted here in red. And I'm just going to put some important characteristic points here. We've got inflection points at 0 and at 2. We have a local minimum located at 3. And we've got x-intercepts at 0 and 4. So the answer to the original question would be the place where our function was decreasing concave up was x is less than 0 and x is between 2 and 3.